and then very happy to share our research for the advanced membrane technology and processes in water treatment. So already Jerry mentioned about my introduction, so I will just skip the introducing myself and go for my class directly.
Yes, thank you, Professor Song. You can.
It's okay, right? Can you see
Yes,
the?
okay.
Yeah.
Yeah.
So this is the today content. For next 2 hours, I will discuss about where is Sydney, and we are University of Technology Sydney. So just a brief introduction of our university, also our research activities. So what Jerry he did in our university, also history of the water management in Sydney, also what's the challenges and future of the water management in our area, and finally I will talk about advanced membrane technology for water reuse and desalination, because wastewater reuse and desalination mainly utilized for our sustainable water resources, and this technology mainly we are utilizing the membrane technology and processes. So if you fully understand what could be the wastewater reuse and then desalination from seawater, so you will have a very good idea of advanced membrane technology and processes. So I will focus on what's our experience in Australia, Sydney, and then discuss about our advanced technology system. I'm not sure how many people have been in Australia in your class. Can you, I'm sure that Jerry has been here. How about how many
Yes.
people visited Australia in the classroom?
Anyone? Nobody.
Nobody. Okay. So I have to explain a little bit more than I expected. So Australia is fourth largest country in the world. So China is bigger than Australia, but we are number 4, and we have 25 million people. So Shanghai has around 20 million population. So Shanghai population lives in this area, and mostly we live in near the coastal area. So this is Perth, Melbourne, Sydney, and Brisbane. Also we have Northern Territory in this area. Also Tasmania, very small island. We consist of 5 the major states and then 2 territories. So Sydney is one of the largest, I think the largest city in Australia. So we have 5 million population. So this is the main metropolitan city in Sydney. So this is the Pacific Ocean, and this is the main city of the Sydney, and we have almost 200 kilometer distance for Blue Mountain, and we cover almost every day a lot of water resource. So most of water is from the Warragamba Dam near the Blue Mountain, the national park. So you can see the little bit of waterways in this area. So we have dams here. So this water is very pure water, because it's a special area for the drinking water supply, and then they submit to the Prospect Reservoir. So this is the reservoir, and then we filtrate our water using the very simple process, which is sand filtration and disinfection. because water is already very clean enough, so that we don't want to remove a lot of natural minerals and then natural fresh water, and it discharged to the Sydney water source. So the problem is nowadays we have a lot of rain because of La Nina. La Nina is the wet condition, so a lot of rainfall is coming. So for last 10 years, we have been very wet, so a lot of raining. But just 20 years ago, we had a very serious drought. So the weather condition due to the climate change is very difficult to predict. So sometimes we have a lot of heavy raining, sometimes we have a very severe drought. So that Sydney, we try to manage our water resource, which rely on the wastewater reuse and desalination. So we have a desalination plant in this area. Also, we have a lot of wastewater reuse plant in all the around the city. So that's how this managed our water resource in Sydney. So today, just focus on the wastewater reuse and the membrane technology for desalination. So this is our university. So we have very modernized buildings. So this is what Jerry, the GIA run. So Professor run study here at the University of Technology Sydney. This is our Faculty of Engineering. So our laboratory is located in the level 12, and then we have also Faculty of Science. So this is the library, and this is the business building. So we have almost 45,000 students working together. Yep. Our main activity is how we can make sure that our nutrient circular economy system. So this is currently we live in the linear economy to the production, use, discharge of nutrient. So we have nitrogen fixation. We rely on the Haber-Bosch process, 2% of the global greenhouse emissions. Also phosphorus, so we rely on the phosphorus mining, but this will run out in 100 years. So we need to look at the alternative. And based on this nutrient, so we produce the food. So nitrogen, phosphorus, and then we consume this nitrogen, phosphorus, and we discharge to the waterways, which is the contaminant. So we need to remove as much as possible to reduce this nitrogen, phosphorus. Also at the same time, in a wastewater treatment plant, so we produce the CO2 and N2O, which are the main greenhouse gases. So we need to reduce the wastewater treatment plant for this kind of the greenhouse gases. So how we can make a linear economy to circular economy? So we want to collect our nutrient, nitrogen, phosphorus before discharge to waterways and produce the fertilizer and produce our food, and then we can consume. So this is the nitrogen and phosphorus resource efficiency we can achieve using circular economy system. So in Australia, so we are one of the agriculture areas, so we utilize a lot of nitrogen, phosphorus, potassium, and then 25% discharge to export to the China, Korea, Japan, or any other East Asia countries. Also we rely on our food from the domestically. So that's how we could look at the nutrient balance. So if we achieve our nutrient from human, for example like urine, and we can observe almost 10% of nutrient, so that we can create the circular economy system. Also, we are developing some membrane in our laboratory, membrane distillation, microfiltration, ultrafiltration, also osmosis, ion exchange membrane, organic solvent nanofiltration. So we utilize the electrospinning, 3D printing, flash sheet, and the hollow fiber machine. So that's the what we can produce the membrane. Also, we are looking at some of the solar powered capacitive deionization. So this is the Tuvalu. Looks like this kind of boomerang style, and they have 25 square kilometer. Population is only 10,000, and no fresh water, so they rely on the rainwater 100%. During severe drought, the water availability can be utilized for this kind of climate change issue. So climate change increased more water sea level, and then they created more problem, even the groundwater, which is collected from the rainwater system, so that water availability is getting worse due to climate change. So that we look at how we can provide the solar power CDI desalination at a small scale. So that's what we are also developing. And then seawater contain lithium. So lithium is one of the important battery element. So we have 230 billion tons of lithium in ocean. So that if we collect the lithium effectively from seawater, so we can cover for our next generation of the battery materials. So we look at our research, how we can collect the lithium and then separate some of the different elements, such as chloride or magnesium. So you can see the lithium can be observed on the CDI electrodes after passing through the cationic exchange membrane. So lithium compounds can be only selectively pass through this membrane, and then we utilize some of the new material to enhance the selectivity of the lithium from seawater, and then developing this technology. So our student is working on this area. Also, we are developing a membrane for organic solvent nanofiltration, which called OSN. Australia aims for a slice of the 61 billion hemp industry for medical and the food product. So this is the hemp. So we call the cannabis. So cannabis contains the cannabidiol. This is the non-psychoactive material, and this is also contain the tetrahydrocannabidiol. So psychoactive extraction can be achieved from the organic solvent nanofiltration. So this is the CBD and THC compound. So when you have this cannabis plant, so we can put this solvent in this cannabis extracted material, and then we want to dissolve the CBD and THC, which is one of the important psychoactive material, and then we can utilize membrane, which is the solvent tolerant membrane, so that we utilize the inkjet printing method to make a better membrane of the organic solvent nanofiltration. So that's what we are working on in this area. So Sydney water, so we have very much short story of the water. So this is the almost wastewater reuse, and then this is in front of our university building. So Central Park. So we have a wastewater plant underground in this building. So almost more than 10,000 people produced wastewater, and then we collect all the wastewater from this building, and we create some of the wastewater reuse. And this is the desalination plant in Sydney. So we have a process to recycle wastewater and then seawater desalination. So these two processes consist of membrane. So in this class, so we will discuss about the membrane, how this membrane make possible to create our opportunity of the recycling wastewater, as well as we look at the seawater desalination. So let me show you. This is the
video.
Yes, I can show you one video. So this is the one of the wastewater treatment plant in Australia. Can you see the?
It's one.
Can you see?
Yes, we can see. Yeah.
Okay. So this is the St. Mary wastewater treatment plant in Sydney. So I can show you the one of their technology. Can you hear the sound?
The Hawkesbury
Okay, that's great.
River is Sydney's largest river system, a beautiful natural icon that is home to thousands of native plants and animal species. The river also to produce up to 50 million litres a day of very high quality recycled water. The water is then pumped to Penrith and released into the Hawkesbury River below Penrith Weir. The St Mary's Water Recycling Plant is a key part of the New South Wales Government's Metropolitan Water Plan. It will play a critical role in increasing water recycling in the Sydney region to 70 billion litres a year by 2015. At St Mary's Water Recycling Plant, the highly treated wastewater from the St Mary's, Quakers Hill and Penrith plants is delivered into the feed water balance tank. From here, the water is then moved through 3 filtration processes for further treatment. In the first part of the process, the wastewater passes through a very fine mechanical strainer. This pre-treatment process removes any particles of organic matter that may still be present. Ultrafiltration is the next stage in the process. The recycled water is pumped into a tank containing the ultrafiltration membranes. A vacuum is applied to draw the recycled water through the semi-permeable membranes. The pores are only 0.02 micron in size, a micron being a millionth of a metre. and allow clean water to pass through, while suspended solids, bacteria and some viruses are blocked. From here, the treated water is then pumped to the reverse osmosis area for a higher level of filtration. The recycled water is forced at high pressure through thousands of smaller reverse osmosis membranes, which are like very fine sieves. At only 0.0005 micron, these membranes trap nutrients, chemicals, bacteria and viruses, allowing only pure water to go through. Within the plant, there are 7 reverse osmosis membrane modules in one pressure vessel, and a total of 528 vessels. That's 3,696 membrane modules filtering the water. After the reverse osmosis, the water is then transferred to the decarbonators. Here it is mixed with air as it trickles down over the filter media called tellerets. This process assists in scrubbing out the carbon dioxide to deliver the final high-quality recycled water. The water is now temporarily stored in the recycled water balance tank prior to the pH level being corrected and final disinfection taking place. From here, it is pumped to Penrith and then released into Boundary Creek. The water, now highly treated to near drinking water levels, enters its final journey and is released into the Hawkesbury Nepean River. The St Mary's water recycling plant will produce up to 50 million litres of highly treated recycled water every day, helping to preserve water in Warragamba Dam while maintaining the flows of the Hawkesbury Nepean River. The project will benefit the wider community, as well as supporting the health of Sydney's greatest river system.
So this is the one of the wastewater treatment plant in Sydney. Let me just so in Sydney we have a lot of wastewater reuse plant. For example, I already show you from the previous slide. So this is the one of
The video is from YouTube.
Still you are looking at, sorry. Sorry, can you see this one?
Yes.
Can you see
Yes,
the
we can see
mic?
this.
Yeah, that's great. So this wastewater reuse plant is a building level. Every day we produce 1,000 cubic meter per day, and then this is what I show the video is the St Mary wastewater reuse plant. One is the very largest wastewater recycling plant. Almost 51 million liter we produce and then recycle water. Also we have Sydney Olympic Park, and they also produced a lot of water recycling system. But difference will be, in this video you may look at we produce the clean water and then we just discharge to the river water system because of clean river water system environment. So we don't fully recycle all the wastewater, and then we just discharge to the Nepean River, and then it will go to our clean environment for the river system. However, in the building I showed this 1,000 cubic meter per day, and this one just produce your wastewater in the building and then recycle and just send it back to your house, which will use for the toilet flushing and laundry machine. So we also utilizing the recycled water laundry machine in the building level. Also inside the Sydney Olympic Park, so we mainly utilize the water fountain entertainment purposes, and we utilize mainly for the toilet flushing. So depending on your purpose, so we have utilized a lot of different recycled waters in Sydney. So currently we have reached to around 30% of recycled water. However, this will be more increasing because of uncertain water prediction and rainfall. So we can utilize the more wastewater recycling because this is cheaper than seawater desalination, almost 4 times cheaper than the seawater desalination. So that if we don't have any serious water resource problem, so mainly the Sydney water, we look at the recycling water. So we continuously improving the how to reuse more recycling system. And let's talk about membrane. The seawater desalination and wastewater reuse, we utilize the mainly membrane process. So membrane is the very useful technology. So what's the membrane? So membrane is the use of porous or non-porous semi-permeable layer to treat water. And this membrane process is a physical separation or filtration process. You have a large particle, small particle, and the small particle will pass through and the large particle will stay. So this kind of physical separation can be achieved, and the separation mechanism can be side exclusion and chemistry, which means that you have a geological geometry size of the different molecule. So some of molecule is the very long chain linear type. Some of them are like some of the circular, like a benzene, or some of the polyphenol related material has different geochemistry. So they have a different static condition, so that they can be separated as a linear type or circular type or different type of the chemistry can be involved. Also electrostatic forces. So membrane, they consist of mainly negative charge because this is the polymer. So polyamide or carboxylic acid or some PVDF, some material, they consist of mainly the negative, so that this will create the electrostatic forces. So minus charge in your wastewater, they will expel from membrane because membrane has a minus charge, and plus charge will be attached on your membrane surface. So they will have a double layer of electrostatic forces for this separation. Also, yeah, there are a lot of different separation mechanism, which is the diffusion. So we will discuss more detail, which is relevant to osmotic pressure for the reverse osmosis, and it is able to solve the most of present problems of drinking water production. So you can remove some of the virus or some of the parasite and pathogens, and that's all can be removed. Also easily combined with the process like absorption or flocculation as a pretreatment. And my target the micropolluter in the future directly for nanofiltration or indirectly by hybrid membrane process using the absorption with the membrane separation system. So membrane process can have a very strong potential, not only remove a lot of microorganisms, but also micropollutants such as pharmaceutical, medical compound, as well as endocrine disrupting chemicals can be removed by this membrane technology. So if you look at what type of the membrane we have, so microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So depending on their size, the microfiltration can remove the most of suspended solid, and ultrafiltration can remove the macromolecules, which has more than 0.01 micrometer size of the molecule, Also, nanofiltration can remove a lot of multivalent ions such as magnesium or calciums or iron or silica. So they can be removed by nanofiltration, and the reverse osmosis can remove the most of monovalent ions such as sodium chloride, and water molecule will only pass through the reverse osmosis. So reverse osmosis can separate all the compound from our water molecule. So that's the reason why membrane processes and technology are very important, because we can recycle water as well as desalinated seawater. So you can see what's the pore size level of the different membrane type can consist of. Also, you can see some of the range of the micromolecular weight, also relative size, depending on the dissolved ions and the organics, and then viruses, bacteria, algae, sand, silt. So coronavirus nowadays is one of the problematic. So they have almost 1 micrometer size. So in fact, they are much, even though it's viruses, but relatively they have a very big size, similar to bacteria, 1 micrometer of the size. So we can easily remove from the microfiltration for the coronavirus. But coronavirus, because of your disinfection in water, chlorine, so easily can deactivate so that if you have a virus in the drinking water, so you don't have to worry about that kind of the region. So we can see the different membrane technology, how we utilize for the membrane applications. So if you look at the microfiltration, so it can be used as an alternative to clarification. So if you look at some of the water treatment plant for drinking water, so you need to remove some of the clay or turbidity material. So people utilize coagulation or flocculation and clarification sediment, and then we need sand filtration and chlorinate, and then you just drink your water. But if you use the microfiltration, so you can replace the 3 technologies, coagulation, clarification, and sand filtration can be maintained from this only microfiltration system. So you can easily control your process compared to this conventional process. So microfiltration is the porous membrane. So commercial MF membrane generally come with pore size of 0.1 micrometer to 0.45 micrometer. And this MF removes the majority of the colloidal or suspended particles from water, and MF is generally used to replace coagulation, flocculation, and sand filtration, significantly reducing water treatment plant footprint, so that you can save a lot of space rather than this kind of very large space required. It also used a pre-filtration or pre-treatment for many other advanced processes, including nanofiltration and reverse osmosis processes. So microfiltration, when you use the pre-treatment, so NF-RO, so this RO process are high pressure membrane, and hence it's important that the membrane operate without major fouling problems, so that the microfiltration or ultrafiltration process are generally used as a pre-treatment to reduce the fouling potential of the feed water before RO or NF process. So MF or UF is used for most RO desalination plants. So this will create the more benefit to reverse osmosis. So this is also useful not only for drinking water or wastewater purpose, but also seawater desalination or wastewater reuse. So microfiltration, ultrafiltration can be used as a pretreatment. So ultrafiltration compared to microfiltration, so what's the difference? So if you look at the size, so 100 nanometer to 0.1 micrometer microfiltration, ultrafiltration is 2 to 50 nanometers. So mostly removes everything that microfiltration can remove, and remove colloidal suspended water, and removes iron and manganese oxide in groundwater. So when you have some of the material from the groundwater, iron and mangan contain very high concentration, but they are within this size with some of the complexation, so that we can remove from this material using ultrafiltration. Also viruses, some of the pathogen viruses can be removed. Microfiltration cannot perfectly remove, but ultrafiltration can remove the mainly cryptosporidium and giardia from surface water. So this is the one of pathogen which is mainly found in your drinking water system. So if you even the chlorination cannot remove because of their pores, so that it's very difficult to remove the cryptosporidium and giardia from the if you cannot treat them for your drinking water treatment plant, so that we need to carefully remove this one. Also macromolecule and such as protein can be removed from ultrafiltration membrane. So nanofiltration, so you can see the nanofiltration, what's the level, 2 to 5 nanometers. So nanofiltration has transmembrane pressure is around 5 to 20 bar. So removes 50 to 70% of the monovalent ion, and then above 95% of the multivalent ion. So you have magnesium, calcium can be removed by up to 95%, most of them, and you can remove sodium chloride only 50%. So nanofiltration is the boundary layer of your size of the monovalent ion and multivalent ion, so that some of the material, like when you have softening water or hard water, so you have too high concentration of magnesium, calcium from your groundwater, so that you want to remove only multivalent, like calcium, magnesium in your water. So you can utilize nanofiltration system, and then you can maintain your minerals from groundwater, so that it can be a very good water mineral sources. So that's the reason why nanofiltration can be used. Also achieves up to 70% permeate recovery rate, 100% removal of the microorganism. So nanofiltration considered capable of replacing disinfection processes. Sometimes used as a pretreatment to RO process to remove the scale forming compounds such as calcium sulfate. So used for water softening to remove the magnesium, calcium that cause hardness. That's the main application nanofiltration can be used. Nowadays the nanofiltration is becoming more important because nanofiltration can be used for the resource recovery from RO brine. So seawater desalination plant, they have a very high concentration of salt after desalinated water. So we have almost 2 times higher concentration of your salt, and then nanofiltration can recover magnesium, calcium, which are more than the multivalent ions size, can be collected from seawater brine, so that you can utilize some of our important sources of the magnesium and calcium. Hello?
Professor Tom?
Yes.
So we have a break between two courses. I think we can have a quick break.
Okay, you want to have a break?
I think it'll be.
Okay.
What do you think?
So if possible, I want to finish the maybe some more slide. Maybe I can finish up to arrow and then we can go next. So I can do one more slide if you agree.
No problem.
Okay, so one more slide I can do. And the reverse osmosis compared to nanofiltration. So reverse osmosis can operate at high pressure up to 70 bar for seawater desalination. So your nanofiltration, you apply the 20 bar, and then the seawater desalination utilize a reverse osmosis 70 bar because of high osmotic pressure of seawater. The seawater salt concentration is almost 3.5%, 35 gram per liter. So this has almost 20 bar pressure of the osmotic. So that this osmotic pressure you have to overcome to pass through your membrane. So this reverse osmosis membrane, you need to apply almost 70 bar. That's the reason why your seawater desalination reverse osmosis has a very, very high pressure and the high energy required. So when you apply 70 bar, so you produce the 1 cubic meter of water, and you need the energy almost 2 kilowatt hours. So 2 kilowatt hour is almost a very high energy consumption, so that the seawater desalination is very expensive because of the high salt concentration with high osmotic pressure. So remove 99% of TDS, 50% of the recovery rate, and removes some 100% microorganism, and membrane is considered non-porous, so that the mechanism is the solution diffusion model will be followed, so that this can be explained. The sodium chloride will diffuse to your membrane, and slowly water molecule only can pass through, and then you have accumulation of your sodium chloride on the surface. So this is non-porous membrane. So compared to MFUF, so RO is the non-porous membrane for solution diffusion model, was mainly used for desalination to achieve the ultra pure water. So people may have a question about reverse osmosis in wastewater reuse and seawater desalination, because people utilize the same membrane, reverse osmosis. So wastewater recycling, we use the reverse osmosis, and seawater desalination, we have a reverse osmosis. So difference is, so when you use the wastewater recycling, so you don't have any high osmotic pressure compared to the seawater. So it's less than 2 bar of the osmotic pressure in your wastewater salt concentration, so that you just use the maximum operating pressure 20 bar, because the problem is your wastewater contain high organics, high fouling. So you can recover almost 80% rather than 50%. So if we use the reverse osmosis in wastewater, So your pore size is a little bit larger than seawater reverse osmosis. So seawater reverse osmosis, wastewater reverse osmosis, even though the membrane is the same, RO, but they have a different pore size depending on your recovery. So that's the difference. You can think about wastewater recycling RO membrane and seawater desalination RO membrane. So after break, how many minutes do we have a break there, Jerry?
I think just 5 minutes. You can just finish this part.
Okay.
We don't have to.
All right. So after 5 minute break, so we can go membrane classification. So we have around 40 slide, and we can go a little bit faster in the second session.
Have a break now.
Yes. So now you can have a
Okay.
5 minute break, and then see you very soon.
Okay. Yes. Okay, thank you, Professor Sean.
Thank you.
Professor Joe has some want to talk with you.
Okay.
Yeah.
Thank you very much for your wonderful discussion for our class. I also learned a lot from your presentation. Yeah. Although, as we know, China is very large, and we will have a lot of technologies to treat our water or wastewater. Yeah, such as we use the membranes. Yeah. As we from your presentation, yeah, I know that in Sydney, yeah, you use a lot of technologies such as membrane. Yeah, in your PPT was that to introduce the membrane. Yeah.
Professor Joe.
Yeah.
Yes. I cannot hear you very clearly. Can you talk near the computer, please?
He's very interested in the membrane part you present in the video, and also previous part, especially in the Sydney wastewater treatment plant.
Very interesting the process that you used in the city, yeah, such as using the filtration and also the reverse osmosis in this process to recycle the wastewater and feed it to the river. Yeah.
Thank you very much.
So it's, yes. Alright. Actually, Professor Joe has some other business to do right now, so he have to leave now. So that's why he asked you some question, and just show his just kind of say goodbye to you at the moment.
All right.
Yeah. That's why we have to have a break at the moment.
Thank you, Professor Joe. It's very great to see you.
Thank you very much.
Okay, we will see you later.
Yeah.
See you later. Yeah.
Thanks.
Thank you. Actually, this is very interesting because this is first time I know about the RO process has a different process in like wastewater treatment and the seawater treatment. I thought they are in the same.
They have more than maybe 50 different types of RO membranes. So
Just why the size is larger than the seawater process? Just for recovery the nitrogen or other things?
Because of you need to remove if you use the wastewater RO membrane, so rejection of seawater is less than 99%. So because the wastewater, you don't need to remove the salt a lot. So they don't want to use a very high rejection membrane. But the seawater, you have a lot of salt concentration. So you need to remove the a lot of salt, so you need to have a very high salt rejection membrane. So they have a different types of RO membrane for seawater, wastewater, even depending on your application, industrial wastewater. So they will have different types of membrane required.
Okay. And I think it's also for some membrane folding.
Absolutely, membrane
It's,
fouling was very, very important because wastewater contain a lot of organics, a lot of high concentration of foulant compared to seawater. So that yeah, you need to make sure that wastewater RO membrane is a larger pore than seawater reverse osmosis membranes.
Okay. Okay. Great. You know, this is actually my first time to organize an like international conference, as a conference seminar or a class via Zoom, first time. And I think this app is a little bit different from Tencent meeting that we use in China. Because you know, still remember last time I called you, and it took around 40 minutes, and the system just crashed because there's a limitation for the basic version.
All right, you're right.
So they allow 40 minutes online.
Oh.
You know, and but this time I just top up some money to the Zoom Pro. Right now we're using the Pro version. So
All right.
at the moment we can continually run this system for more than 2 hours.
You should have talked to me because I can generate the Zoom meeting, right? So that it doesn't have to worry about your spending of the Zoom Pro.
Yes, yes. But the problem, you know, it's very urgent because when I found this thing just in this morning, just around 10 a.m. today. So I think it's too late to like announce other people and you to inform you about the changing another, you know, Zoom ID. So that's why I just yeah, spend some money by myself. Yeah.
So,
But it's good,
so do you
right? Especially
have you received my email for the PDF slide?
yes, yes, I already received
All
it.
right. So
Because when you sent me the email, I was in this classroom and settled down everything, you know, including the laptop and also the system.
okay.
Because we are in the classroom, we use the projector, and also I put another video. You can see that. You can see our students.
All right.
I put this. I'm just self-made video presentation for the, you know, for the classroom sighting. You can have a look. Look at that.
Wow, that's a lot of yeah screen you have.
Yes.
Right?
Then I put the chair on the table and put my phone between two chalk box
Okay,
to set it down, make it fixed.
I see.
And also, I borrowed a power bank from our students.
All right.
Otherwise, it will not take such a long time.
So, do you ask a student do they have any questions so far?
Yes, I think some student will ask you some questions.
So
but it's not deliberately arranged. I think they just spontaneously have some problem, some question to ask you.
okay. So if you don't mind, we can have a 1 or 2 question before we start.
Do you have any questions right now? Ask one. Thank you. All right. I think they are too shy at the moment, but I think they will ask you later.
All right, that's okay. That's fine.
Yes. Yes.
So
The one who asks your question will get a high score in this class, you know.
do you think that my talk is too fast, or is it okay to understand, or they understand my talk, or what's going on there?
I think I'm okay. What do you guys think? All right. I think it's good.
Okay, that's great.
I think
That's
good.
great. Yeah, if you don't understand, please let me know. Yeah, I will speak a little bit slower.
Yes, yes. Actually, before starting this class, I really asked Professor Sean to speak slowly to like present this lecture. I think maybe because some like professional terms like in membrane or other technologies, I think maybe you are not familiar with it. So I asked him to speak slowly and explain more and more details. So I think you guys can understand what he's talking. Right.
So you already
I think
had a membrane class in Chinese, right?
it's not membrane class. It's just a basic class for the advanced water treatment technology and in water treatment. And this chapter is mainly about the membrane.
All right.
So it's not membrane class. It's like the whole class for the municipal engineering for the water treatment like department. So this student like for different direction, maybe someone is working on wastewater treatment, someone in drinking water treatment, and some are focused on coagulation or some wastewater treatment. Someone are in the membrane technology. This chapter, I know you are the expert in this area, so I would like to just invite you to give this like presentation. And also, this is also the first time that's my student to have the opportunity to catch a international class. So I think for both me and them, it's like a very new and experienced like just a very unique experience. Yeah.
Thank you.
So I think it's great.
Thanks, Jerry.
Yeah. Eh. Okay, I think we can just come back to our lecture. I think already more than 5 minutes break.
Yeah.
Okay, so let's go back to the lecture. Let's welcome to Professor Sean to continue his presentation. Thank you.
Okay, thank you, Jerry. Let me share my slide. So next slide is Jerry. Do I have to finish exactly 10 p.m. or what's the time? Do I have to very strict for the time or a little bit relaxed?
I could be a little bit relaxed.
Okay.
If you have some other things to do, we can just finish this part earlier, and I can do actual donation for students.
Okay. Okay. So yeah, I can finish on time. So we have a membrane classification in terms of nature and structure, geometry, transport mechanism. So nature is a sensitive or biological membrane. So your body, like your skin or your hair, they're all the biological membrane. So this we call the biological natural membrane, and they're sensitive, like organic or inorganic. So we have ceramic, metal, carbon, zeolite, glass. Membrane can be produced also structure. So we have a symmetric, which is the very much equal from the active layer to support layer, and asymmetric is not the symmetric, so which means not equal on your active layer and then support layer. It's very different, such as when you have a reverse osmosis membrane, our membrane consists of CTA, cellulose triacetate, cell symmetry membrane, or the polyamide membrane, thin-film composite, so which we call asymmetry membrane. So mostly asymmetry membrane is the more frequently used for your reverse osmosis membrane, and they have also integral asymmetry or composite, so which contain some of the different component of the polymer. So we just say composite membrane. The geometry, tubular tie, hollow fiber, flaccid. Transport mechanism is dense or porous. So porous membrane, they have a mechanism, not cell diffusion and molecular sieving and the selective surface flow. So dense membrane, mostly RO membrane or nanofiltration membrane, follow the solution diffusion or facilitated mechanism we have for dense membrane. So if you look at the photo, this is more clear. So this is the flaccid and spiral round module, and this is the pressure vessel, and this is pump, and then membrane is spiral round module is inside. Also you can see the plate and flame element type of your membrane module. So it can be used different purpose. For seawater desalination, wastewater RO membrane is spiral round, and then this hollow fiber or flaccid flame module is a membrane bioreactor or just microfiltration, and this is a hollow fiber. The hollow fiber looks like your hair, so they have a pore size in this hollow, and then you have a microfiltration, ultrafiltration, and then water is in, out, in, or into, out. So you can select the sum of the option. So it looks like they have this kind of tubular type inside, a lot of fiber existing, and then you just put as a cassette in your wastewater tank, and then you can utilize as a submerged hollow fiber membrane module. So this is the membrane design. So flaccid, hollow fiber, tubular, how you can make some design. Then symmetry membrane, uniform pore size and thickness, resistance to mass transfer. Asymmetry membrane have dense, high selective top layer. So as I mentioned, asymmetry, they have this kind of active layer. So we just say polyamide layer is on the surface, and then at the bottom we just have a support layer for your active layer. So we can create the different way of the asymmetry or symmetry membrane for your membrane configuration. Also you can see the how membrane same images of different types of the membrane. So you can see some hollow fiber. So you have a support layer, the water molecule will pass through this one, and this is some material, different material on the flaccid type. So you can see some of the micrometer pore size on the PVDF membrane. Also some of the ceramic membrane, you can see the different types of structure, and you will have a separation structure of your membrane. So that's how it looks like your pore size, and you can control your membrane in terms of different polymers. So membrane fabrication, so mostly commercial membrane are made of organic polymers. So mostly PSF, PES, PVDF, PP, polyamide membrane. So they are utilizing as a RO membrane, some of them. This is the ultrafiltration membrane. This is the PVDF is microfiltration or ultrafiltration membrane. So depending on the polymer, so you can make a different size of your membrane. Also some of them utilize as a supporting layer. So polyamide RO membrane, this is the salt rejection layer, on the top of polysulfone. So this is the ultrafiltration membrane, and then we can put the RO membrane on the top of the PES or PSF. So depending on your designed membrane, so how we can make a different size of membrane. Also, this is the thin composite membrane layer, generally consists of the polyamide. So this polyamide are formed by the process called interfacial polymerization. So this is automatically they will try to polymerize using MPD and TMC. So this is the monomer, and this is the organic solution as a TMC, and then these two polymer they combine together and then will create the interfacial polymerization to produce the polyamide RO membrane. So that's the reaction you can do, and the polyamide layer can reject up to 99.9% of dissolved salt from the water. So this polyamide membrane is most important RO membrane. So you can produce the most of RO membrane consists of this polyamide. So depending on their concentration of MPD, TMC, and depending on their temperature and then their time polymerization, so you can create the larger pore of wastewater RO membrane or very high rejection of the seawater membrane of RO. So that's the how we create the membrane. So you can see the I'm sure that you have experience lab scale fabrication. So this is the casting knife. They put the polymer and then you can just slide, and then you will have this kind of polymer membrane. So like in the egg fry, so you put your eggs, and the egg is protein. So this protein you just heat, and then you will create some of the egg fry like this kind of type. So this is the industrial scale of membrane fabrication. You can produce even hollow fiber. You can see the hollow fiber membrane produced. So you have a polymer and the water as a soaking bath, and then you will create this kind of membrane. And most of membrane, they have a problem for the fouling. So fouling is the accumulation of unwanted deposit on the membrane surface, and accumulated deposit can cause internal fouling. So they will clog your pore size of membrane. So we just call surface fouling, pore blocking inside the pore. So you will have less flux and then low performance. So membrane fouling reduces the membrane efficiency and productivity, and it is one of the major challenges of any membrane process. So you need to control this membrane fouling. So membrane fouling consists of inorganic, organic, and biofouling. So colloidal fouling, calcium, alumina, silicate, and membrane scaling, magnesium, calcium, phosphate, and calcium and carbonate, sulfate, calcium carbonate, and calcium sulfate, magnesium carbonate, and silica can be accumulate on the surface of your membrane because of their solubility saturated. So that we need to make sure that how we can reduce the inorganic fouling and the organic fouling. So in wastewater, there are a lot of polymers, proteins, polysaccharide, humic, fulvic, carboxylic acid, EPS, so that it causes the pore blocking or surface membrane fouling blocking. So organic fouling has to be also cleaned up in a certain stage when you reduce your membrane performance. Also biofouling, so some of the bacteria like sulfate or aerobic bacteria, fungus, yeast, algae, so they have a direct attack of membrane surface, so that they grow on the membrane surface. It's like a biofilm will be generated on the membrane surface because there are a lot of nutrients to eat from this bacteria. So we need to remove this kind of fouling. So physical, chemical, biological cleaning is very well established to restore membrane performance once fouling has occurred. So physical cleaning, so backwashing. So you have a lot of foulant on the surface, and then you just push it through the backwashing. So water is go reverse way, and then you will reduce a lot of fouling as physical backwashing with the compressed air. And chemical cleaning, so acid washing, basic washing, specific chemical. The acid washing is very much useful for the inorganic fouling, and the basic washing is very much used for organic fouling. And the specific chemicals such as oil. So you have oil on the surface of membrane. So this oil can be removed very well with surfactant. So surfactant can be used as a chemical cleaning for specific chemical, and bio or disinfection cleaning can be used for your mitigation of the membrane fouling. So depending on your feed water quality and your operation of the membrane, so we have a very well established physical, chemical, biological cleaning method, so that you can utilize this kind of a process. So fouling prevention or reduction also can be achieved by operation at below critical flux of the membrane. Also disinfection or use of biocidal to prevent biofouling, and biocidal or disinfection cleaning, treatment of the feed water to remove foulant such as primary sedimentation and coagulation. Also optimize the membrane cleaning frequencies. So that's how we can achieve the membrane fouling for wastewater reuse. And now I want to focus on advanced membrane technology and process in terms of seawater desalination. So let's see one of the video, which is the Sydney desalination plant. So this is the Sydney desalination plant. So you can see what process we are utilizing in Sydney. Can you hear the voice for this video?
Yes, yes.
That's great.
So where is the desalination plant?
Desalination plant.
Isn't it? It's which part?
It's
Next to the
near the
airport.
airport. So you can see the. Okay, I will show you the. What is the?
Quite strong. Can you hear
Let
me?
me show you the. Okay, this is the Sydney. Yep. So you can see the. Just a second. Okay, so I will show you the what is the desalination plant. So this is Sydney. So we have airport here, right?
Okay.
Yeah,
Kingsport.
Kingsport Airport. And then so Sydney desalination plant located here.
Ah, I know. It's
Right.
I didn't see the.
Because when you land your flight from China to Sydney, and then you can see the your desalination
Actually,
plant
Alicia
here.
An is associate professor at the School of Energy Environment, City University of Hong Kong, and leading water and membrane technology laboratory. Dr. An received her PhD in civil and environmental engineering at the Hong Kong University of Science.
Okay, sorry, this is the another. Yeah. Okay, so that's the Sydney desalination plant here, and then I just to show you the Saint Mary wastewater reuse plant. So near the Penrith. So I just to show you previous wastewater reuse plant located in this area, Saint Mary wastewater reuse plant, Penrith.
That's very far from the city.
Right, it's almost 100, I think the 200 kilometers from city, and then they recycle water and then discharge to the river and then collect here to supply. Sydney desalination plant located in this area. The main.
I know this is the national park.
Sorry.
Is this the desalination plant next to the national park?
Yes, you are correct. That's the Cronulla National Park located here. So you can see there are a lot of trees and then a lot of bushes.
Maybe.
So they collect the seawater from the Tasman Sea and then supply it to Sydney main metropolitan cities. So Warragamba Dam is here. So they are all connected like a stem level. So depending on your dam level, Sydney desalination plant, wastewater reuse plant. So we have a lot of the interactive water resource from the city.
I just know it in Beijing, not in Sydney.
Right, I think the Beijing has no seawater, right? That's the.
We don't have water here.
So that's the difference from Sydney. Yeah.
But we also, I think we also have the wastewater recycle system. The plant.
Okay, you have a lot of recycle plant, yes, but not seawater desalination.
Not seawater desalination, but we have another project like a north water transfer to the north part.
All right, I see.
We have a very big project.
Okay, that's great. So yeah, so that's the how we are operating the different membrane technology. Most of them are consisting of membrane technology. So I just want to continue. For any other question do you have, Jerry?
No.
Okay.
No. We can
So we can continue for the desalination. So a lot of desalination is keep growing because of uncertain the climate change as well as a lot of population. They like to live near the coastal line and then they need more water resource. And that's the Sydney desalination plant started from 2008 because of severe drought. So you can see the very much severe drought from the Sydney desalination was established in 2008. The capacity is 250 million liters per day. It's almost 250,000 cubic meter per day. So it was $2.1 billion, and then first operation, and currently it's shut down because of the La Nina. We have a lot of rainfall at the moment, so that it's completely shut down at this moment. But if you look at for last 250 years in Sydney, so you can see the drought, severe drought. Yep. So whenever we have a drought, the red colors, so we establish the dam or create some of Sydney Olympic Park, or we had a desalination plant. So that's the how this works for the overall the desalination related activity. So we cannot make any more dams since 2000. That's the reason why we have relied on more desalination plant or wastewater recycling. So that's the membrane technology is becoming more important because they are the very much main technology to recycle wastewater. So we have 6 very big desalination plant in Australia, and then this is the Sydney desalination plant. So you can see from the airplane near the airport. So 200 million liters per day. They have almost 45 hectares, and then 25 kilometers from Sydney Central Business District. And then this one has intake and then drum screening, dual media filtration, micro cartridge filter, and the arrow membrane, and then post-treatment, lime, and fluoride, and the carbon dioxide remineralization have been used for this desalination processes. So you want to understand membrane technology. So what kind of membrane we can use? So you can see this is the Sydney desalination plant, pre-treatment, arrow membrane, post-treatment. So we can see how this membrane can be applied. So membrane can be used for pre-treatment as a dual media filter or microfiltration, ultrafiltration, and reverse osmosis can be used as a membrane technology. So you can see how this is possible to use. So you need to understand better for your seawater. So seawater contain very high pH compared to the drinking water, around 7.9 to 9, because they have a lot of the compounds is dissolved in the salt. So that based on this kind of pH, so you have mainly pH 9, this bicarbonate mainly consists of in your water. So CO2 is less than 8, and then bicarbonate and carbonate. So when you have a CO2 concentration increased in the air, so nowadays a lot of climate change is the CO2 is the major problem. So when you have more CO2 in the air, so your pH will be decreased more and more in your seawater, and then you cannot make some of the your seawater ecosystem or animal or some shells. So that that's another problem. So seawater, they have different characteristics of CO2 and the bicarbonate and carbonate. Also pH is around 8, and then because of the climate change we have also more problem for this seawater. And then pre-treatment from this seawater we adjust the different pH, because this pH has easily you can hydrolyze, which means the hydroxyl compound can be combined with the calcium, magnesium, iron, which will give a very high inorganic scaling system. So pretreatment comparison, dual media filter. So you can see how the conventional, like a dual media filter, compared to ultrafiltration membrane. So we can utilize the one of method, but ultrafiltration method is the more reliable and then more clean. Your feed water can be produced to make a better quality of the reverse osmosis. So ultrafiltration can be used as a pretreatment on behalf of the dual media filter conventional process. So capital cost and then some of the fixed cost, so total cost $0.01 per cubic meter and $0.02. So also the cost is not that much different compared to conventional process, so that the ultrafiltration is also very much easily you can apply for this process. Also, this is the one of the problem of the some anti-scalant inorganic scaling. So before RO membrane, so you extract your water molecule from reverse osmosis membrane. So you have a very high concentration of salt, so which means calcium in seawater will combine with carbonate. So you have a calcium carbonate on the top of the RO membrane. Also, you could possibly create the magnesium carbonate. Also, you may have a calcium sulfate can be produced from your RO surface, so that the anti-scalant surface active material that interfere with the precipitation of this kind of material, so that we can think about what kind of inorganic scaling would be useful. Sodium hexametaphosphate SHMP is a hexamer composition, so sodium phosphate. So this is the one of the anti-scalant you can incorporate, or some of the organics like EDTA can be used as a anti-scalant, so that depending on your inorganic scalant, so we can select any anti-scalant to have a better quality of the inorganic scaling control. So that's the how we can make sure that the inorganic scaling. And dechlorination. So we have a chlorination because we want to prevent the biofilm on the pipeline, even media filter or pretreatment. And before you discharge your chlorinated water, so you need to dechlorinate, otherwise the polyamide polymer membrane on the RO membrane will be damaged. So that we need to dechlorinate. So we put the SBS, sodium metabisulfite. So this will be used as a chlorine SBS 3:1 ratio, and then this will create this kind of formula, and then you can remove the active chlorine dose, so that you can prevent your RO membrane. That's how we can protect. Also, demineralization after RO membrane. So you need the post-treatment with lime or some of the water, because we remove the most of what salt in your RO system. So sodium chloride, every salt will be removed, and then very pure permeate will be generated. So post-treatment with lime. So post-treatment with lime, so you have a little bit of post-treatment system has to be combined with the WHO recommend 10 milligram per liter of magnesium. 30 milligram per liter of calcium for drinking water. So we put the calcium carbonate or calcium hydroxide. So here lime is more about calcium compound, and then magnesium can be combined together. And two solutions are widely used to mineralize the naturalized water. So CO2 can be added in your water, so can be carbonated, changed to the calcium carbonate, magnesium oxide, and then sodium carbonate, so that this can be useful for remineralization of your water. So seawater desalination, you need the post-treatment, which require some of the mineral can be incorporated in your clean water system, and then you can discharge to your drinking water, tap water system. So annual operation cost, so this is energy. Mainly when you operate seawater desalination plant, because of the osmotic pressure, energy require 51%. And then indirect cost, monitoring, maintenance, labor cost, and waste stream disposal required for O&M. And then this is the very important for water parameter for your seawater. So you need to look at very carefully what's the concentration of the turbidity, organics, SDI, total suspended solid, iron, manganese, silica, chlorine, and then temperature, oil and grease. So that compounds will damage your membrane processes. So based on the seawater, mostly they are very clean, but some of the water has a very high concentration of different water parameters, so that you can try to maintain using the pretreatment method. So one of them is salt dense index, but I don't think this is important in this class, so I will just skip this one. And then you can see the hardness, phosphate, TDS, and then barium sulfate, strontium. It is also very much important for your designing of your system. Also, when you design your membrane, so in fact you don't have to utilize your manual calculation. So we have already very well established software. So it's provides a free software. So every membrane company like DuPont or Toray or Origin Water, Beijing Origin Water, so I think that they have developed some of the software to predict your design of the membrane. So you have a lot of useful information. Feed water quality you put there, and then you will get all the information from your water parameter, and then put the reverse osmosis, and then you can design how many membrane you need, what kind of membrane rejection. So all the compounds can be calculated from your simulated software system. So we have utilized this kind of software to design your reverse osmosis process. So if we look at the RO membrane history, so it has been developed for last almost 70 years, since 1950. So first the seawater desalination plant using the reverse osmosis. Before that, people utilized mostly distillation. So in Middle East country, there are a lot of oil. So this oil can be burned and produced a lot of distilled water. So people utilize the distilled water before they have reverse osmosis membrane, and then they started from 1956, 1970, and then first energy reduction is a reverse osmosis membrane. So Dow Chemical, Dow Filtech, so they have developed the first breakthrough of the innovation, reverse osmosis membrane, using polyamide polysimping company membrane. So before 1970, so people utilized the cellulose triacetate RO membrane, which was not really high performance, high rejection of the seawater desalination. So it was not useful for overall application of your seawater desalination. But 1970, polyamide RO membrane was first innovation period for SWRO. And then in 1990s, almost 2000, they have some progress of the energy reduction using energy recovery device. So second technology innovation, it happened for energy recovery device. So energy was used 4 kilowatt per cubic meter of seawater desalination. So previously, before we developed this one, so it was 10 kilowatt hour per cubic meter. But after this energy recovery device, so we significantly reduced an overall energy consumption for seawater desalination. That's the reason why the SWRO, seawater reverse osmosis, has been dominant, and then distillation process has been reduced significantly from 2010. So in the future, we need to look at another significant technology innovation to improve the overall membrane technology processes, so that we can have a more cost-effective and then high performance seawater reverse osmosis technology development. So if you look at the reverse osmosis membrane, already we discussed about this one. So this looks like RO membrane. So you can see almost the skin layer. This is the most important skin layer to remove your overall salt, sodium and chloride. The skin layer is a 20 nanometer. It's a very skin polyamide thin film composite, and this is the, we just say, polysulfone support. So this is the polysulfone ultrafiltration membrane support your skin layer. So this role is the polysulfone ultrafiltration membrane will have your supporting role, and then you have a backing layer. So this is the backing layer as a nonwoven fiber, so that you can protect your high pressure, because they have to tolerate around 70 bar pressure from this pressure element, so that you need to have a very small skin layer, support layer and backing layer. And then mainly they utilized as a osmosis diffusion. Already you have a osmosis concept. So you have osmotic pressure depending on your natural. This is the cherry. So you have a cherry. Cherry contain very high sugar. So high sugar has osmotic pressure. For example, like sucrose. When you have a 1 gram per liter of sucrose sugar, it has around 1.5 kilopascal. So when you have rain water, then you have a very high concentration of sugar in your cherry. So your skin layer on your cherry will penetrate because of the osmotic pressure. So water is penetrating to your overall cherry inside, and then this is swallowed, and then finally this will be burst, so that you will damage your cherry. So that's how osmotic pressure will create, and then different sugar concentration, seawater concentration, every salt will contribute to your osmotic pressure. So that this is the main problem of your, and this is the Bandt-Hoff equation. So who developed this one? Pi is equal to concentration of salt and the ideal your gas constant, and this is the temperature, and this person got a first Nobel Prize in chemistry. So this simple equation, pi equal to CRT, has a very high impact to calculate the overall osmotic pressure. So that he got the first Nobel Prize in chemistry, and this is seawater desalination. So we have a seawater concentration and brine with the 50% of the recovery, and then this is the water permeate, and this is the 50% recovery we have achieved, and the overall energy consumption is almost 3.5 kilowatt hour per cubic meters. So we need to look at the concentration polarization. So this is membrane. So you have a salt concentration. This is all the dot are salt concentration. So you pressurize. So water is permeate. And then your salt cannot pass through. So you have a keep accumulate. So your osmotic pressure overall on the surface of membrane, and then pure water, you have a very high osmotic pressure compared to the bulk osmotic pressure condition. So sorry, yeah. Let me have a little bit of water.
No worries. Take your time.
So your real osmotic pressure concentration has a very different from membrane surface, and then your water permeate, pure water. So based on this concept, we just say concentration polarization. So you have to calculate all the detail from your real concentration polarization. So this is pressure vessel. You can see that it consists of fiberglass or stainless steel, up to 8 spiral round elements in a vessel, and vessels can be arranged into banks with desired number of stages or passes. And this is the overall seawater desalination energy consumption. So total energy use 3.9 kilowatt hour for production of 1 cubic meter. So you have an intake around 0.2 kilowatt hour, pretreatment like microfiltration, ultrafiltration, or some of dual media filter, and then you have a reverse osmosis membrane, and you can have a discharge to the ocean, and then product line. So most of water production energy consumption is the highest in reverse osmosis, around 72%, which means reverse osmosis, if you can reduce the sum of your energy consumption, so you can significantly reduce your energy cost. So let's look at the energy calculation. So this is a very simple. You can do based on your pilot demonstration or theoretical calculation. So let's look at the theoretical calculation first. So you have a 70 bar applied pressure, and then your flow rate of the water is 3 cubic meter per second. Typical feed pressure for high salinity, and then your pump efficiency is 80%. The consumed feed pump energy can be calculated. Energy W is equal to your flow rate, 3 cubic meter per second, and dP is how much pressure you want to apply, and then pump efficiency 80%, 0.8, so 3 and 70 bar, 7,000 kilopascal, and you will have around theoretical energy consumption is 7.29 kilowatt hour per cubic meter. So this is the theoretical calculation, but we are utilizing the energy recovery device. So you can see the sum of the energy recovery saving can be achieved from overall your energy recovery turbine or energy recovery pressure exchanger. So this is the more about the pilot scale. So before you start your real design of the seawater, so you can have seawater flow rate, pressure, recovery, permeate. So you have operate this one for a long time, and then you have a real power consumption without energy recovery device. So let's say your energy consumption is 300 kilowatt. The specific energy your recovery is 40%, so that you will get 7.5 kilowatt hour per cubic meter. And then when you use the power energy recovery turbine and the energy exchanger, so you can save the 50 to 60% energy saving. So that's the how you can reduce the power. So theoretical power was the 7.3 kilowatt hour per cubic meter, and based on your real operation with the energy recovery device, so you have saved your energy cost almost 50% or 60%. So let's look at the energy. So this is the power consumption. So you have your light bulb 100 kilowatt normally, then you have operate 10 hours during your night time, then we just say 1 kilowatt hour, and you have a 10 times 100 watt, 1000 watt, which is 1 kilowatt, times 1 hour operation is 1 kilowatt hour. So which means, so in Australia we have 1 kilowatt hours. So just a small light bulb costs around $0.3. So desalination plant, as I mentioned, so you need 4 kilowatt hour per cubic meter for reverse osmosis. So let's say Sydney desalination plant, as I mentioned, 250,000 cubic meter per day. So every day we need the energy cost $290,000 because of the energy cost is very high. So if you save the 1 kilowatt hour from this one, you can save the almost three-fourths of the your almost 25% of energy cost. If you reduce to kilowatt hour, so 50% of the your energy cost can be saved from this seawater desalination plant. So that's why when you consider, when you produce desalinated water 4 kilowatt hour, so how many light bulb can be utilized? So you can guess how the desalination process is very expensive. That's the reason why most of Australian desalination plant, they utilize the renewable energy, which is the wind farm. So that's the we are trying to operate. Also, as I mentioned, the theoretical energy consumption was 7.3 kilowatt hour per cubic meter. However, when you operate your process with energy recovery device, so you can save almost 50%. So that's the second innovation of the seawater desalination plant, because we utilize this kind of the energy recovery device. So I will show you how this energy recovery device works. Then hopefully you can also think about how the innovation can be achieved from your technology. So let me okay, can you see?
Yeah.
60% by the PX.
So this is the reverse osmosis, how the energy recovery device is working to save the 50% of your overall energy cost.
When seawater reverse osmosis, or SWRO, was first introduced, the membranes required very high pressure, pumps were inefficient, and control systems consisted of throttle valves that wasted energy. However, by far the greatest loss was the pressure energy leaving the process in the concentrate reject from the membranes. ERI's PX pressure exchanger recovers nearly all of the energy from the membrane reject stream and feeds it back to the SWRO process. Using just the energy in the reject concentrate, the PX pressurizes new seawater for the membranes, reducing the high-pressure pump flow requirements. This not only saves energy, it reduces the size and cost of the high-pressure pump. The reject concentrate from the SWRO membranes flows to the PX, where pressure energy is transferred directly to incoming seawater at up to 98% efficiency. Pressurized seawater from the PX, circulated with a small booster pump, joins the stream from the high-pressure pump. The energy consumed by the high-pressure pump, which is by far the largest operating expense of an SWRO plant, is reduced by about 60% by the PX. The PX is simple yet elegantly designed. The housing contains a ceramic rotor, the only moving part in the device. Surrounding the rotor are a sleeve and two end covers. These ceramic components fit snugly around the rotor, forming a tight seal that prevents pressure from escaping. Low-pressure seawater enters the PX and fills the rotor. This seawater is then exposed to high-pressure concentrate from the membranes. Pressure transfers directly from the concentrate to the seawater inside the rotor ducts. Spent concentrate leaves the rotor at low pressure, pushed out by fresh seawater. The rotor is turned by the flow itself, spinning at approximately 1,200 rotations per minute. The ducts of the rotor function like a carousel, charging and discharging as the pressure transfer process repeats itself. Water in the narrow gap around the rotor, which serves as a lubricant, is continuously replaced and refreshed. Mixing between the concentrate and seawater is minimal because the exposure time is so short. Overall, the PX Advanced Energy Recovery technology is the most efficient, easy-to-use, reliable solution to affordable desalination today.
So that's the how the energy recovery device works, because this device really saved the overall energy cost of the seawater desalination. That's the reason why the most of plant in Middle East and then any other country, they utilize the seawater reverse osmosis process rather than distillation. So that's the second breakthrough. So seawater desalination, first breakthrough was reverse osmosis membrane using polyamide thin film composite membrane. And then second breakthrough is this energy recovery device. Because of this two technology, so seawater desalination is very much popular nowadays. So what's the next innovation? And that could be resource recovery. So as I mentioned from the beginning of my presentation, so we have a lot of mineral in seawater. So if you look at the seawater mineral concentration, this is the lithium. So lithium concentration is almost every day 17 kilogram is coming through this seawater. And then after reverse osmosis, so we have increased lithium concentration almost 9 times, like 9 kilogram per day. of the leading concentration. So we can look at the mineral from seawater can be recovered from the RO brine. So you can see lithium, magnesium, some of the useful compounds, rubidium, can be obtained from seawater. And then if we have technology to recover some of the useful resource recovery, then we can have a better seawater desalination for our innovation. So if you are interested in your research, looking for some of your interesting research topic, so this is the area you may consider for your future career. So thank you for your attention, and then very much appreciate your support for this kind of the lectures. And then I'd like to share one photo with Jerry. So he came to UTS. It was almost 5 years ago, 6 years ago, and then he joined our university as a PhD student, and he got a problem for the pandemic, for the coronavirus, for almost 2 years, and then he got a job, and then he want to work together with us. And this is our some virtual kind of graduation ceremony without any official ceremony system. So it was a very good timing together with Jerry for your PhD, and then I'm very happy to see you have growing very well for your career. Also, he met his wife in Sydney, so he got a job and family in Sydney, and then now he's working very hard at the Beijing University of Technology, and then we are very much proud of you, and all the best for your future career. Also like to thank you to the student for your attention, and then if you have any questions, I'm very happy to take your question.